Now what we're going to do is look at some of the basic operations that we can do to a specific matrix. That is, we're going to look at what's called the row operations, which is something like basic matrix algebra. Now, that's not to say that we're going to be looking at combinations of matrices just yet. That's the sort of thing we'll get to later in this chapter with stuff like adding and multiplying matrices together. For now, what we're focusing on are the basic things that can be done to a single matrix to adjust it and maybe clean up the picture a little bit, make it a bit clearer what it is that we're trying to do, get closer to a solution or what have you for what we're doing with the matrix. And bear in mind that when we're doing this stuff, what we are doing is essentially the same sort of algebra we work with when we're adjusting a system of equations, because at least for what we're seeing here, that's where all of this comes from, really. So, for example, the first operation that we look at is denoted with these Ri and Rj symbols. What these represent are row I and row j. We get a little bit abstract with our notation when we're talking about matrices, just to try and be as general as possible, where what this talks about is exchanging rows. So that is taking one row and switching it with another. So for example, if we have that matrix from before, the one that we've been trying to solve, and we applied to it the operation that switches rows 1 and 2, R1, 2 arrow, R2, what we would do is take those first two rows, row 1, row 2 there, and we would just flip them. We would exchange the two rows. In the exact same way that if you have a system of equations, you can reorganize the equations however you like, because sometimes it's a little bit clearer to see the picture that you're aiming for when you have one on top or one on the bottom instead of being in the middle. Now, it's kind of natural to look at that and think to yourself, well, if we can exchange rows, why can't we just exchange columns? And the reason for that kind of comes from where this was. Instead of thinking about the coefficients, let's go back to thinking about the equations just for a second. And if we're thinking about exchanging columns instead of rows, what we'd be doing is taking the coefficients and reassigning those to different variables. Now, technically speaking, yeah, you could do that. You'd also have to rearrange how you think about each variable within the system and push a whole bunch of terms around, but sure, technically it would work, it's just it wouldn't really do anything at best, and at worst, it would make the whole thing a confusing mess. So we don't talk about exchanging columns, really. It doesn't fit what we're going for here. Instead, we look at row exchanges. The next one that we look at is multiplication of rows. So if you take some constant k and multiply it by row I, so some row in there, that's what row sub I refers to. This is just constant multiplication. And the way that constant multiplication works for matrices, is essentially a abstractification, feels like a word, might not be a word, of the distributive property. Because if you have some equation and you want to multiply a value in through the equation, you got to multiply every single term one by one. Works the exact same way here. So if we have that matrix and we want to say multiply the, what was I looking at here, third row, I guess, I don't know why I picked that one, by -2, what we would do is take the matrix, apply that operation where we use that notation with the arrow to notate that we're taking an operation, and then we put the operation above it because, well, I'll talk about that in a second. But we take that operation, and in doing so, we multiply all the terms out, and then we condense it down a little bit to get our new matrix with that constant multiplied in, like so. And then from there, our last one is kind of a combination thing, where for the last operation, we're taking a bit of a more complex operation. It's got not quite the same sort of nice notation, so I'll just call this the linear combination, because that's technically speaking what it should be called, where what we do is we take constant multiples of some rows and add them to other rows. This is essentially the elimination process, where if we've got one equation on top of another and we want to knock one out, we can add it into the other one to see if it cancels some of those coefficients, just like what we did in that first example. This is kind of a condensation symbolically of that idea of working with direct elimination, except it doesn't always eliminate in quite the same way. But anyway, for clarity, let's just think of another picture in terms of that matrix that we've been working with, where we start with it, and then let's think about subtracting 2 times the third row. And I picked minus 2 times R3 because we've already done that multiplication there, so we have a sense of what the picture is going to look like. But when we're doing that sort of thing, we don't take the first operation first and then the second. We sort of squish them together. And what's going to happen is we'll take all of the elements of the first row, and we will subtract from them 2 times each of the elements from the third row. And as a result, when we take that action, we'll end up with a value, or not a value, a matrix, something like so. Now, it's important to note here that with these arrows that I have, we're always taking 1 or maybe 2 basic row operations. And when we do that, we get something that is called a row equivalent matrix. Now, it's important to say that row equivalent is not the same as equal. Very clearly, these are 2 different matrices. They got different numbers in them. Can't be the same if the numbers aren't the same. But in a sense, they represent the same system. That is to say, if we took everything in here and turned it back into a system of equations, and then did the same thing over here, we would get the same system up to whatever adjustments we made. So whatever solutions this one might hint at that that one doesn't, will still solve both. And because all these were basic operations, even though these are all fairly different for the most part, they're all row equivalent. They all have the same meaning in terms of our ultimate solution, in terms of our ultimate goal with this kind of problem, which is to find values x, y, and z that satisfy all 3 equations at once. And as a result, when we're working with this, what we can do, what we're going to try to do, is see if there are ways that we can make our system simpler using these row operations to get to a place where we can either directly substitute or just get our values as they are. And I'll say that with this stuff, it takes a while to get used to this. The hard part's not really the math, because looking at all this math, it's move number, multiply number, add number. Like, this is elementary school stuff. But there's a lot of it going on, and you have to be careful about where you put what thing, and the order makes a huge difference. You have to be really careful pushing these things around and making sure that everything goes in the right place. So it takes a while to get used to, but just bear in mind that when you're actually doing the math itself, it's not so bad. You just have to really pay attention and work slowly to build up your comfort with these kinds of constructions. I think you will be able to get there with a bit of practice. And in our next bit, we're going to talk about how you can approach these problems so that you can actually build towards one of these solutions that we actually want.